Hello, I am Karush, and I will be presenting on surprise minimizing multi-agent learning with energy-based models. This is joint work with colleagues from University of Toronto, Borealis AI, and RBC Capital Markets. Multi-agent reinforcement learning systems enable learning of policies using the centralized training and decentralized control paradigm. This has proven to be useful for exploiting value-based methods which motivate collaboration across agents. However, increasing number of agents are faced with sudden changes in the environment. These sudden changes lead to abrupt shifts in agent behaviors. This phenomenon of a sudden change in agents' beliefs about the world is termed as surprise. In the case of multi-agent learning, surprising states grow with the increasing number of agents. While conventional methods minimize surprise using planning and search, these become computationally expensive and brittle in multi-agent settings. Instead, we suggest that surprise minimization can be cast as an energy minimization problem. We unify surprise with free energy in the multi-agent setting. We construct a temporal EBM which represents an estimate of surprise agents may face in the environment. We first define a surprise value function which quantifies the degree of surprise agents may face in a given state. We then use the log sum exponential function as our energy operator to estimate energy. Our theoretical result highlights that the log sum exponential operator is a contraction mapping. Finally, all agents jointly minimize surprise estimate utilizing temporal difference learning with the estimate as joint intrinsic motivation. Jointly optimizing for surprise across agents leads to a stable objective, which is easy to train. Intuitively, Q values of agents are penalized if the energy in a given state is high. We implement our energy-based scheme using a novel architecture built on top of the Q-mix algorithm. Learning of surprise in a high-dimensional value function space is cumbersome due to the large number of actions. To simplify the problem, we use local value encoders to encode the agent value functions in fewer bits. We then encode the joint world state into a lower dimensional representation. Next, we account for uncertainty by encoding the standard deviation between consecutive states. The state deviation encoder models the changes in subsequent states without constructing an explicit model of the world. Finally, representations obtained from encoders are used to estimate a distribution of surprise values. The distribution represents the density of states wherein an agent may encounter most surprise. We sample from this distribution, use the log sum exponential operator to compute energy, and minimize surprise using stochastic backpropagation. We demonstrate the effectiveness of our energy-based scheme in StarCraft 2 micromanagement and predator-prey benchmarks. Given the right temperature parameter, MX agents stabilize learning by minimizing energy. MX agent performs consistent with recent methods in multi-agent learning. MX agents produce surprise robust policies which prioritize to minimize the damage while maximizing returns. Agents coordinate to seek low risk states which help them defeat the enemy. Check out our project webpage or visit the poster booth to know more about our work. Thank you.